Welcome to the tutorial for Automotive System Design. I'm Sokotani from Nessus Electronic Corporation. Here is my brief self-introduction. I got my MS degree from Waseda University and a PhD degree from Kanazawa University. I joined Mitsubishi Electric Corporation in 1995. I was a visiting scholar at Stanford University, and now I'm a processor architect in Renesas Electronics Corporation. My current research interest is an application-specific processor architecture ranging from IoT devices to automobiles. Here is the outline of this tutorial. In this tutorial, we'll discuss what are the requirements of automotive system design for in-vehicle devices, and how can we implement them from a processing perspective. First, I will explain automotive system trends and automotive semiconductors as an introduction. 4 key technologies are given at the next section, which is composed of computing for automotive issues, in-vehicle network, safety and security, and maintenance and upgrade. Finally, I will summarize my talk. Now, I will start from the introduction. The automotive industry is undergoing major changes in 3 key areas. The first is a connected car, which is constantly connected to the internet and the cloud services. This is a foundation for improved convenience, but it is also strongly required to counter cyber attacks. The second is automated driving. Advances in AI technologies and in-vehicle electronics have led to the practical application of Level 3 and Level 4. The third is electric vehicles. With the need to reduce greenhouse gas emissions, the growth of this market is becoming more accelerated. Adding services to 3 key areas, automotive system trend is said to be CASE case. Looking at the 3 key technological areas from largest to smallest changes in the market. Electric vehicles will increase up to 8 times by 2025. Sensor content will increase up to 5 times in automated vehicles. Telematic installed vehicles will double by 2025. To meet the requirement, the in-vehicle EE electronic architecture will evolve. Systems require higher real-time processing performance, network topology development, enhanced safety, security, and secure OTA. The current flat distributed architecture reduces harness weight among ECUs, electrical control units, by relocating functions. The distributed architecture will evolve first into a domain architecture that's logically reconfigured for each domain, and then, in the future, into a physical reconfigured zone architecture. Processors are being developed based on the overall architectural flow. In most current in-vehicle electronic control systems, each functional domain is generally controlled independently, and each function is controlled by an MCU at the end of the system. In this domain architecture, each function will be integrated into domain controllers. The table shows typical domains and the corresponding functions. In the future, each domain controller will be integrated into an in-vehicle computer that controls the entire system. This table shows the levels of autonomous driving defined by SAE, Society of Automotive Engineers. It shows what the features do and what the drivers must do at each level. The roles of both drivers and features change greatly starting at level 3. The features change from driver support to automated driving. A connected car is always connected to the internet and cloud services. The drivers have used only pre-installed services. The information exchange is limited, for example, for maintenance services. From now on, the goal is to provide add-on services for all vehicles. Once connected to an existing wide area network to receive services, the car will have the same features as smartphones. Cars are connected to wide area networks through vehicle-to-vehicle communications, roadside-by-road communications, and intelligent transport systems. So the in-vehicle network needs to be aware of its connection to those networks. This is why the safety and security aspects are so important. We will move to on the topic of electric vehicles. There is a strong market demand for EVs due to stricter CO2 emission regulations and so-called climate change countermeasures. Last summer, New York Times reported that California will ban the sale of new gasoline cars by 2035. But then, a few days later, there was news about a temporary ban on EV charging due to electricity shortages. EV market development will only be possible if battery energy storage technology and their reliability are resolved. Nevertheless, the evolution and expansion of EV-related technologies will undoubtedly continue. Next, let's look at the classification and requirements for automotive semiconductors from the processing point of view. With the introduction of in-vehicle electronic control systems, cars will be equipped with many embedded devices. Embedded devices include MCUs, microcontroller units, SoCs, system on chip. MCUs are general purpose and used for system control. They have a power supply and clock inside the chip, and use embedded memory semiconductor process with non-volatile memory SRAM. Flash and analog components are also on the chip. SoCs are for image processing and communication. They provide performance for arithmetic operations in specific applications. SoC use logic process with SRAM and have large external main memory. The process is selected based on the balance between cost, quality, and the performance of consumer products, which is of course not a leading-edge process. So far, this is a general classification. In addition, devices for automotive applications also have automotive-grade high-level reliability and high-temperature operation. As embedded devices in automobiles, MCUs were initially adopted for engine control and now have expanded to SoCs. This is a classification of automotive semiconductors. This table shows typical device and network types applicable to each domain. SoCs and Ethernet are used for data processing for ADAS, ADS, and infotainment. MCUs and CAN, control area network, are used for powertrain, chassis and safety, and body, with emphasis on real-time performance. This slide illustrates an electronic system of an autonomous driving system. Many cameras and sensors detect and transmit environmental information. The car infotainment system uses cognitive computing to process data. Advanced vehicle control tightly interfaces cognitive computing and human-machine interface computing to react to changes in the external environment and to detect drivers' instruction and status in real time for safe driving. Power devices and sensing devices are not included in this tutorial. We'll focus on car infotainment systems, advanced vehicle control, and in-vehicle networking. Let's have a look at the requirement for semiconductor devices. The left figure shows a rough image of performance, MIPS, and the power efficiency, MIPS per watt, for a typical embedded device categories, MCUs and associates. The diagonal dotted line represents power consumption. To achieve both low power consumption and high performance, domain-specific development is important. The balance point of application depends on the field. MCU SoC selection itself is a domain-specific development. It is the architect's work to make the best design selection according to each application. The main strategy to achieve this is to employ dedicated hardware. We will see various dedicated hardware in this tutorial. The balance point between power consumption and performance varies depending on the application. But in the embedded field, low power consumption is an absolute requirement. Power limits are constrained by thermal dissipation cost, package, and the power environment. Let's look at an example of power consumption requirements for an automotive MCUs. The integration of many functions into one MCU requires increasing the density of the semiconductor die, which can be realized by process technology improvement. Furthermore, the power consumption of automotive MCUs must be single-digit watts. Under thermal constraints, because cooling methods such as water, air cooling, and thermal sheet cannot be used in ECUs. So far, we have looked at trends in automotive technologies, CASE case, and E-architecture is important for devices. In response to the megatrends listed here, in-vehicle systems face the following technology challenges. For example, AI computing performance for advanced recognition and judgment, multi-control performance for intelligent control, high data rate communication for in-vehicle networking, high reliability mechanism, safety and security, over-the-air for maintenance upgrade to get new application. The next section describes how these challenges are addressed with the requirement for low power consumption and good real-time performance. We will start computing for automotive ECUs with car infotainment associates. Automotive information systems have evolved from a car navigation systems to ADAS, advanced driver assistance systems, and automated driving. The use of AI is being promoted to resolve the feature differences from ADAS to AD. Since 2012, DNNs have become popular as an approach to visual perception. AI in vehicles is viewed as machine perception for object recognition and tracking. This demo video shows a multi-camera obstacle and road feature detection using 5 cameras for autonomous driving level 2. The system uses a single forward-facing camera for vehicle, pedestrian detection, segmentation, and traffic sign classification. 4 surrounded view cameras are used for vehicle, pedestrian detection. This slide shows software architecture for lane detection, one of the road feature detection, in the front-facing camera system. The image data input from the camera is distortion corrected and resized by the image renderer. And then, image formatting is performed by the computer vision engine. The CNN IP performs semantic segmentation and then performs lane detection in CVE. The result is overlaid on the display image. These functions for autonomous driving are designed to meet the new car assessment program requirements. In Level 3 and higher automated driving, the in-vehicle computer takes over the driving that was previously performed by the driver. Therefore, in-vehicle electronic control systems need to become more sophisticated. In an automated driving system, however, each function will be integrated into a domain controller. Each domain controller will be integrated into an in-vehicle computer that controls the entire system. Automated driving systems need to control all functions and require high AI computing performance. This is the CNN, convolutional neural network processing performance estimation required by the automated driving function. To ensure high level of autonomy, the number of sensors per vehicle is increasing. Data from each sensor is processed by multiple CNNs for recognition, segmentation, and other applications. In order to output actuation commands from the information from the sensors, it's necessary to process these multiple CNNs in a time frame of about 100 milliseconds. Assuming that the information input from each sensor is processed approximately 30 times per second and there are 20 installed sensors, the entire system would require a CNN processing performance of at least 120 TOPS, teleoperations per second. However, the higher the computing performance, the higher the power consumption. Among the electronic devices installed in EVs, the control unit for automated driving consumes the largest amount of power. This is because as the level of automation increases, information from many sensors must be processed. The cost impact is significant. If the cooling system is changed dependent on the automated driving system installation, air cooling is desirable for ECUs. Therefore, high AI performance and power efficiency to achieve air cooling are technical challenges. This figure shows benchmarked AI processors for each application, which includes data center processors, in-vehicle processors, and very low power processors. Each processor is plotted with CNN peak performance on the vertical axis and the peak power on the horizontal axis. The air cooling is possible with total ECU power consumption of 25 watts or less. Let's assume that half of 25 watts, around 12 watts, needs to be allocated for CNN processing. The performance target of 60 to 120 TOPS with a power efficiency of 10 TOPS per watt hits the sweet spot for automated driving systems. This is an example of a CNN processor for autonomous driving. 3 CNN accelerators and a large scratch pad memory are connected by interconnects, capable of wide bandwidth and low latency data transfer. Compared to GPGPU, this architecture enables high execution performance efficiency of CNN processing and improves power efficiency by reducing the amount of data transferred to and from external DRAM, which is the power eater. The theoretical maximum of 66 TOPS in a single device's LSI is based on the practical approach to cost and implementation in the 12-nanometer process. Here is a detailed block diagram of the CNN processor. It's implemented with 32 by 16, 27-bit precision mark, multiply and accumulation operators, major activation and pooling functions. Now we will move to vehicle control MCUs. The basic operation functions of automobiles are moving forward and backward, turning and stopping. To realize these functions, motors are put to various uses in autonomous cars, such as in traction motors, electric power steering, and electric brake systems. Motor control is a critical technology. There are also combustion engine vehicles, but I will talk about the popular EV. This figure shows the basic components of an electric vehicle: an inverter and a motor. The inverter consists of a motor control MCU and an IGBT driver. The IGBT driver is an inverter circuit. A power semiconductor device acts as a switching device to control power. Noteworthy points of electrification is improvement of energy efficiency of drive system. However, compared to gasoline-powered vehicles, current battery-powered electric vehicles are still not as user-friendly. Because of the short cruising range, the distance that can be driven on a single full charge of a new battery, which is 500 to 600 km, two-thirds that of gasoline-powered engine. The benefits of EV motors are excellent motion controllability, and the simple mechanism is suitable for downsizing and weight reduction. This slide shows the torque characteristics and the driving characteristics of engine vehicles and electric vehicles. The left graph shows the engine characteristics with the horizontal axis showing angular speed and the vertical axis showing torque. Internal combustion engines can only produce large torque at medium speed. The right graph shows the vehicle characteristics with the horizontal axis showing speed and the vertical axis showing driving force. The red dotted line indicates vehicle requirements: large torque at low speed and a constant output at middle to high speed. A multi-stage transmission is needed to bridge the gap between engine characteristics and vehicle requirements. Compared to internal combustion engines, EV motors have characteristics that are well matched to vehicle requirements. So, we can make an EV motor system without complicated mechanics. Just add one reduction gear between the motor and the wheel. The motor can also rotate in reverse, eliminating the need for a reverse gear. The engine can only rotate forward. That is why motors are suitable for automobiles. This figure shows the basic principles of an EV motor control system. The motor rotates when electricity flows through the windings of the motor. In order to point torque commands from a vehicle controller, a feedback control system is realized with monitored input data such as current and rotation angles of the motor. A synchronous motor is driven using information from an angle sensor attached to one end of the rotor. To generate torque, the stator windings are energized to create a rotating magnetic field that matches the position of the rotating rotor. A motor control MCU generates PWM signal as gate drive controls to drive a high voltage IGBT driver, which drives an EV motor with 3 alternative currents. The shape of the PWM signal is carefully controlled and varied to improve motor efficiency and reduce heat generation by reducing switching losses. Field-oriented control algorithm (FOC), as shown here, is the most popular type of algorithm that can achieve highly efficient motor control. To calculate the optimum PWM duty values, FOC contains compute-intensive functions, including coordinate transformations, series of matrices. Therefore, MCUs for motor control are required to have high computing power. This MCU architecture for EV motor systems with motor control accelerators achieves 0.8 microsecond high-speed field-oriented control processing (FOC), which can cover future SRC power devices. The accelerators autonomously execute basic motor control operations and offload them from the CPU. The green arrows indicate the flows of the motor control. Sensing data at the AD converters or the RD converters is directly transferred to the motor control accelerators. The motor control accelerators allow the CPU to execute advanced control algorithms to reduce the energy consumption of the motors. The CPU can also run at a low frequency with a low CPU load, which results in optimal thermal design of the LSI. Performance improvement by applying the motor accelerators is shown in the right graph. The motor accelerators offload motor control processing from the CPU, and the CPU load decreases from 65% to 1.2%. The functional safety tasks are executed with a periodic verification of the motor accelerators. The rest of the CPU resources can be used for advanced motor operations. Next, we will move to in-vehicle networking. In-vehicle networking technology is the backbone of every electrical feature in today's vehicles. The automotive industry, together with technology providers and standardization bodies, has developed specialized communication protocols or made extensions to existing standards to meet the demanding requirements, especially reliability of the automotive domain. CAN, Controller Area Network, is the most used protocol for low and medium speed automotive control applications such as powertrain. When CAN was invented by Bosch, bit rates of 500 kbps and 8-watt payloads were sufficient. Today, with very similar technology, CAN XL supports transmission speeds of 10 Mbps and payloads up to 2 KB. In the early 2000s, Ethernet was introduced to the automotive industry for onboard diagnostics and audio-video applications. Applications in the audio-video domain require advanced QoS, quality of service, in the Ethernet endpoints. These requirements are defined in a set of specifications and are known collectively as audio-video bridging (AVB). Another advancement in Ethernet technology that has expanded its use in automotive environments is the development of the full duplex physical layer technology consisting of a single twisted pair. This robust physical layer started with support for 100 Mbps and meets demanding automotive requirements. Today, transmission speeds are supported up to 10 Gbps. The scaling in recent years has not followed a strictly upward trajectory, and efforts have been underway to fill the gaps between the lower throughput protocols and the faster technology now coming to market. In parallel to development targeted to achieve automotive compliant transmission speeds for multi-gigabit interfaces, a special technology for automotive with 10 Mbps speed is available. Aided by this technology, control and advanced driver assistance system ADAS functions or automated driving AD can be realized, connecting cameras and other sensors, actuators, and data processing ECUs to a switched Ethernet network. To achieve low latency and the QoS requirements of automotive applications, IEEE has enhanced the AVB specification set and published it under the name TSN, Time Sensitive Network. The TSN specifications achieve bounded latency and reliable networks. So, CAN XL and 10BST1S are two new actors in the networking arena. In vehicle network architecture, we also follow the evolution of EE architecture. Currently, the system is the central gateway stage, where the number of ECU is increasing more than 100 as the amount of data handled increases. The next stage will be the in-vehicle server domain architecture, where the amount of data will increase due to the addition of ADAS ECUs, and the spread of gigabit Ethernet will accelerate. For full-time cloud connection, an in-vehicle application server will be introduced so that network traffic can be suppressed effectively. In the future, the architecture will evolve to the vehicle computer zone architecture stage, which is expected to further increase time amount of data transferred. As an intermediate step, In the evolutionary process, in-vehicle server domain architecture is being considered by each market car maker, and it's assumed that a part of ADAS, IVI, in-vehicle infotainment, and body control functions will be integrated into in-vehicle server in the future. In this proof of concept, in-vehicle server performs video application processing as well as routing processing. The three applications are DVL, DMS, and body control. The in-vehicle server CPU performs real-time encoding for DVL and face detection for DMS on the video input from the camera. In addition, CAN signals for motor control and vehicle condition from the CAN analyzer are input to the in-vehicle server via MCU. This is the actual configuration using the evaluation board. Now please see the actual demo in action. First, let's start with DVL. The recorded video is saved to eMMC memory along with the real-time display. The saved recordings can be listed and any recording can be played back. The second is DMS. When the driver is seated, the system first detects the driver's face. If it is determined that the driver is talking on the cell phone, falling asleep, looking aside, or smoking, and the water is displayed. The third is body control. Vehicle condition data and motor control data are input to in-vehicle server via MCU as CAN signals. Vehicle condition data is stored in eMMC memory, and motor control data is routed to motor control. Next, I will describe safety and security. Let's begin with functional safety. The word safe is defined as having no unacceptable risk. What is functional safety? Intrinsic safety is a method for ensuring safety by removing the causes of danger. Functional safety, on the other hand, is a method of reducing risks to an acceptable level to ensure. As an example, let's consider what measures to take to prevent a train and a car from colliding when a road and railway intersect. Achieving intrinsic safety involves eliminating the inherent dangers of intersecting railways and roads by using overhead crossing to eliminate the possibility of collisions between cars and trains. In contrast, functional safety considers methods such as establishing a railway crossing to reduce the likelihood of a collision. It entails installing a barrier and alarm at the intersection of the railway and road. Although in this method, railways and roads still physically intersect, railroad crossings are installed to reduce the risk of collisions to an acceptable level. This embodies the concept of functional safety. ISO 26262 Road Vehicles Functional Safety is the automotive industry standard. The more general IEC 61508 is intended for industrial plants and is not suitable for mass-produced products such as automobiles. Therefore, functional safety standards specific to automobiles were established in 2011. Risk is defined as bodily harm to traffic participants due to loss of EE system functionality. Given a malfunction of a defined function at the vehicle level, for example ABS, anti-lock braking system, hazard analysis and risk assessment for each safety goal at vehicle level follows. This analysis is based on the exposure, severity, and controllability of the hazard, and the resulting risk, and to determine the ASIL, Automotive Safety Integrity Level A to D, that is, the level of risk reduction needed to achieve a tolerable risk. All of the phases of the functional safety life cycles are defined and documented in this standard. Of course, automotive devices, hardware, are also required to support this. ISO 26262 covers the entire product life cycle, but today we will focus on hardware design. Malfunction of the EE component is classified into two types of failures. Systematic failures represent the failures in an item function that are induced in a deterministic way during development, manufacturing, or maintenance. Random hardware failures appear during the lifetime of a hardware element and emanate from random defects innate to the process or usage conditions. The concept of functional safety has emerged because it's necessary to make things based on the premise that people make mistakes and things break in order to avoid serious accidents. A safety mechanism is a technical solution implemented by EE functions or elements, or by other technologies, to detect faults or control failures in order to achieve or maintain a safe state. Examples of safety mechanisms are ECC, error correction code, hardware redundancy, built-in self-test, and several others. The effectiveness of the solution to detect these random failures is measured by three metrics: single point fault metric, latent fault metric, and failure rate. The primary goal for hardware component is to achieve the ability to detect random hardware faults as specified in each ASIL. Next, I will describe the safety-assisted hardware that enables the safety mechanisms. Let's look at fault tolerance for ADAS and AD features. There are two possible behaviors of the automated driving feature when a fault is detected. The first is a fail silent, which stops all functions and enters a silent state. The second is the fault tolerance, which switches to the backup and continuous processing. The backup system will initiate a minimal risk maneuver aimed at reducing risk. In realizing these systems, using an SoC MCU with LCD has advantages in reducing cost, power consumption, and system complexity. The devices with LCD can detect failures by self-diagnosis. The fail-silent system can be realized by the LSI alone. And the fault tolerance system can be built by combining the LSI and the backup functions. On the other hand, LSI with less than HOD has a low detection rate of failures. It is necessary to duplicate the LSI in highly reliable systems, such as autonomous driving. I'd like to talk about other safety mechanisms applied to the chips by using an SoC. The most intuitive scenario associated with architectural features is to have redundant elements. dual core lock step (DCLS) is used because an LSR is required to have a failure detection system to meet HOD. Running two processors together in lockstep allows us to very easily meet the requirement for the safety critical functions without timing overhead. The basic elements composing a DCLS system are two CPUs, master core and checker core, and a set of comparators that detect a failure by continuously comparing CPU's outputs. There is a cost overhead in having two CPUs, but it is well understood that some devices need the real-time capability. However, the implementation of dual-core lockstep to achieve the SOD metric requires several considerations. Dependent failures that cause the same error across redundant logics will result in the same output, and thus the failure cannot be detected. Reducing the occurrence of dependent failures is essential. In this case, the following four measures are effective. First, the master core and the checker core are placed separately. This prevents crosstalk between the main core and the checker core. Second, applying delay processing so that the checker core operates a few cycles after the master core. This reduces the occurrence of dependent failures due to clock jitter and noise. Third, adding a clock monitor module. The clock monitor detects clock instability on the redundant logic for checking it's working as a safety mechanism or not. Last, applying EDC, error detection code, to the input signals. If an error occurs in the input signal, it cannot be detected by dual-core lockstep and would affect subsequent processing. To prevent that, this module applies an EDC check to the input signal of dual-core lockstep. An EDC generated to protect the output signal is also applied. I will introduce the other safety mechanisms. EDC is used for error detection of data stored in SRAM in chips and DRAM in the external memory. The extended Hamming codes, single error correction, double error detection, and BCH codes are applied according to the use case. The safety mechanisms applied to the interconnect inside the SoC are shown. Since the interconnects can functionally be regarded as a communication network of the SoC, safety mechanisms based on the communication flow model described in ISO 26262 are applied. The table shows each failure mode and the corresponding safety mechanisms. They are configured end-to-end and can detect faults that occur in the transmission path. Here is an example of module-by-module access control. The interconnect assigns a safety ID to which a source module belongs to each transaction. A transaction with an authorized safety ID is allowed to access to the target module. And the module shared by multiple tasks, such as DMARC, the memory protection table in the MMU, Memory Management Unit, is used to isolate memory areas for different tasks. This figure shows an example of how each functional module of the SoC is assigned to the use case of the automotive driving system. Data processing from each sensor in the first half in SOB, while route planning and vehicle operation in the second half is in SOD. The reason why the second half is in HUD is that if a hazardous event occurs due to a malfunction of the automated driving system in vehicle operation, it will be almost impossible for the drivers to avoid it. Several functions such as CNN are in both processing in HUD and processing in HUD. It is desirable to have a safety mechanism that can switch priority between processing performance and safety performance depending on the applications. CNN1 and CNN2 performs as dual-core lock step only when executing the HLD task. This video shows an overview of the architecture of the chip for automated driving, and the modules to which HLD was mapped on the previous slide are shown in green. In the previous SoC for driver support features, the modules with a high ASIO target are only in the control domain, indicated by the dotted red line. In autonomous driving SoCs, the HUD target modules are spread across the SoC. Next, I will explain field-based. The hardware architecture metrics described so far do not include timing constraints. The complete evaluation of the safety mechanisms shall involve timing performance. In fact, the system must be able to detect faults and transition to a safe state within a specific time, fault tolerant time interval, FTTI. Otherwise, the fault can become a system-level hazard. This figure also illustrates the diagnostic test interval, DTI, the part of FTTI allotted to detect the fault. The DTI is defined based on the application requirements. This table shows an example of device field test methods for in-vehicle applications other than software testing. We can see there are different methods depending on the domain and issue requirement. Field-based, a self-diagnose function is executed in the field after manufacturing test. To test an automotive LSI, the field-based is required to meet several constraints, including the specified metric and the limited test application time. Field-based can diagnose the safety mechanisms to achieve the required latent fault metric. Power-on self-test is executed during each driving cycle to detect faults in the safety mechanisms, which is done during the chip power-on procedure before starting any function operations. To meet both the hardware and the test application time requirement, based with time slices adopted in SoCs for driver assistance systems during runtime. BIST is activated periodically so that faults can be detected during runtime. Rapid progress automotive architecture will lead from the systems in lower ASIO to the systems that require highest HUD in the near future. For example, up until now, the body system has been realized in SUV. However, advanced body systems that meet HUD have to be considered due to the trend of integration of ECUs. Automotive MCUs also need to follow this trend. In this figure, the upper row shows the field based of the chassis and safety MCUs and the powertrain MCUs. The lower row shows the field based of body-controlled MCUs. Once a vehicle is parked, the MCUs in the vehicle are powered down, and the chassis and safety system and the powertrain system. On the other hand, the MCUs for the body systems are not powered down even while parked. Any opportunity to apply power on self-test are lost. To solve this problem, SR-based, sleep resume-based, which is executed periodically in sleep mode, was proposed to enable BEAST with the time slice while parked. SR-BEAST can be executed while the MCU wakes up periodically to check vehicle status, including keyless entry. The SR-BEAST is executed during the sleep resume period to avoid disturbing a CPU processing period. The SR-BEAST is required to meet the limited test application time. During the sleep period, oscillators are stopped to minimize power consumption. The long oscillation stabilization time of the crystal oscillator exceeds the wake-up time requirement. Therefore, the SR-BEAST uses an on-chip oscillator as a source clock instead of crystal oscillator. This on-chip ring oscillator stabilization time is only 8 microseconds, which is sufficiently short for a wake-up time requirement. Furthermore, due to backward compatibility of ECUs, the current fluctuation of vehicle control MCUs is required to be less than or equal to existing MCUs. If the scan clock frequency was too high for quick testing, the peak current fluctuation arises due to the shifting operations of scan chains. To solve this problem, the MCU has a suppressor of peak current fluctuation in scan chain. Next, I will mention virtualization-assisted hardware. Integration of multiple electronic control units (ECUs) reduces vehicle weight by deleting the wire harness between the ECUs used for the in-vehicle network, resulting in energy savings. This ECU integration leads to microcontroller unit, MCU integration. Many functions have to be squeezed into one MCU and associates. The integration of ECUs also mixes software components with varying safety integrity levels in one LSI. Resources isolation is inevitable for functional safety to prevent software interference. Virtualization, which was originally used in mainframe and server for more secure systems, spread to embedded systems. Virtualization is realized by emulating virtual hardware on physical hardware. However, developers have been avoiding the use of virtualization with automotive control applications because it has a negative impact to response time. The left figure shows the software architecture of the virtualization. The hypervisor is software which can provide the OS with virtual hardware, which creates virtual machines, VMs, and controls them. Software on each ECU runs in an isolated VM. Data and time interference among VMs is prohibited by using virtualization. The overhead of the hypervisor disturbs real-time response in vehicle control system. The right figure illustrates two types of hypervisor overhead. The first is the VM context switch time. When there are two VMs in one CPU, one VM is active and the other is in the background. The hypervisor switches the context of the VMs each control period. The second overhead is the interrupt distribution processing time. When an interrupt request to a VM occurs, the hypervisor disturbs the interrupt to the virtual machines. Virtualization-assisted processor can reduce these overheads by a register bank that immediately switches system registers required for hypervisor. The hardware also has an IRQ affinity control interface, which specifies the VM services for a given interrupt. So I will describe security in the next section. Vehicle hacking is when someone takes control of your car or some of the car's auxiliary systems remotely. FCA failed to classify automotive jailbreaking is an example why in-vehicle security is necessary. Here is an overview of what happened. Company B's MCU controlled the vehicle via CAN. The car was designed to be able to communicate with the outside world via Company A's MCU. This was the entry point for hacking. Hackers found that software of Company B's MCU was backed up on Company A's MCU, so they replaced this backup software and updated Company B's MCU software. This allowed people to remotely control the car through the network. This hacking could have been prevented if CAN message authentication, OTA over the air, or secure boot had been supported. This triggered an immediate discussion on the importance of a car security. Vehicle vulnerabilities have been exploited for many years. In 2010, experimental security analysis of a car was presented by University of Washington. In 2015, well-known black hat security report Jailbreak was issued and resulted in 1.4 million records. In 2016, researchers remotely hacked Tesla Model S. In 2018, researchers presented that the visible but inconspicuous perturbation that only perturbs the object, such as a road sign, which can reliably cause a DNA-based classifier to make a classification error. This attack was able to cause the classifier to interpret a physically subtly modified stop sign as a speed limit 45 sign. Recently, clone attacks have also been reported. Let's move on to automotive security standards. In order to address automotive security, some discussion was started in Europe, trendsetter in this field. EVITA, major European security project, is one of the outcomes from those activities. Cybersecurity threats have been growing in recent years with the rapid connectedness of automobiles. In response to these developments, the UNECE Regulation Cybersecurity UN R155 and ISO SAE 21434 Cybersecurity Standard for Road Vehicles was established and enforced. I will explain EVITA later in the next few slides. This slide shows EVITA e-safety vehicle intrusion-protected applications overview. In order to provide authentication functions to existing ECUs, it's important to keep key management for authentication secure. Hardware security modules prevent unauthorized operators from the outside by implementing key management and important functions such as cipher generation and random number generation for authentications in a hardware-independent secure zone. Hardware security modules for in-vehicle ECUs have been developed by the European Hustler Initiative software for secure hardware extension and by the e-safety vehicle intrusion protected application EVITA project. Hardware key management and encryption processes are designed to maintain a secure environment, reduce software processing load, and take into account the limited processing resources and the cost of in-vehicle issues. In particular, EVITA specifies 3 levels of HSMs, elevator full, elevator medium, and elevator light, depending on the security level required by each issue. Please note that full, medium, and light do not correspond to security levels, but correspond to use cases. Elevator full is for securing external vehicular communications. Elevator medium is securing internal communications and IP protection. And elevator light is for securing critical sensors and actuators. This table summarizes elevator HSM and SHG functional requirements with the latest future trends for your reference. First expansion, larger key lengths, public key method, algorithms that are highly compatible with cloud are required in the future. Elevator is a de facto standard in hardware specification. Please note that elevator is just a necessary condition for automotive security, but not a sufficient condition. We need to consider system security together with elevator HSM, depending on actual use cases. In-vehicle information systems and in-vehicle control systems will be increasingly linked to the cloud. This slide shows an example of various data flow in a connected car. There are domains in the automotive system such as sensing, cognitive, infotainment, and vehicle control domains. They are connected to the cloud through an in-vehicle application server. If you look at the data flow, you will find there are many communications between each domain and the cloud. From the sensing domain, sensor data and the sensor status are sent to the cloud as big data. In the cognitive domain, autonomous driving software is downloaded from the cloud to install state-of-the-art algorithms. Between the control domain and the cloud, some vehicle status information is shared, which is reflected to reliable and safe driving. As you see, connected cars provide a safe, comfortable driving experience, but we have to consider security threats at the same time. Here we need to consider security threats regarding sensor data. For example, if LiDAR data is manipulated by another car, the car may collide with an object. For cognitive, if the learning database is falsified, misjudgment may occur and could cause a severe traffic accident. In the infotainment domain, malicious applications may be installed, resulting in private information theft. Regarding the control domain, malicious firmware may be installed, which causes hijacking or unstable or inefficient vehicle control. Security threats have increased due to constant connection to the cloud and the sophistication of applications. Advanced security measures are necessary to realize safe and secure vehicles. We needed to consider a defense in-depth approach because an attacker looks for an easy entry point first. In automotive systems, the attacker may think of external network hacking first, then message hacking, ECU level hacking, and MCU level hacking. External network hacking is relatively easier than others. We can use IT-based security techniques such as firewalling, secure end-to-end communication, intrusion detection system, or intrusion prevention system to protect external network. We will see CMAC in CAN communication against message hacking. In order to prevent spoofing or data falsification, CMAC, cipher-based message authentication code, is used in in-vehicle network. Illegal access into in-vehicle network can be detected and eliminated. High-speed crypto is one of the important factors to implement CMAC in bus communication in order not to degrade system performance. The target speed depends on the use case, so careful design is necessary. In order to protect the firmware of the ECU or the MCUs, secure boot is commonly used. Secure boot is a security technique to prevent software falsification, malware, and information leakage from boot code. Boot code is verified by using CMAC, which ensures no falsification. Finally, I conclude this chapter with a summary of the overall safety and security analysis. In the development according to ISO 26262 functional safety and ISO SA 21434 cybersecurity, we believe that the analysis should start from the same safety goal. This allows us to harmonize the analysis for each standard. If safety analysis and threat analysis have different goals, the analysis may lead to the opposite result, that is, a safety-threatening analysis. For example, forced shutdown by tamper detection may be dangerous in some cases. The analysis will be based on use cases. Next, I will explain today's final topic, maintenance and upgrade. Over the air. OTA is firmware and software updates via wireless communication without bringing your car to a car dealer. Recently, control codes stored in MCUs are getting more and more complex and large scale. Therefore, shipping a car free from a software bug is challenging. Furthermore, control code can be updated for performance improvement and upgrading functions according to new applications and standards. This figure shows an example OTA operations. Two code areas are provided in one embedded flash memory in MCU. Code area A stores execution code before the OTA update, and area B is unused. Firstly, new code is programmed in area B, and the execution code area is swapped from area A to B by flag setting charge during the ignition off period. After ignition is on, a new code is executed. This slide shows key challenges for OTA. The first one is memory density overhead. It's from buffer memory for temporarily storing new code, or two-plane configuration to store both new and old codes, as an OTA operation example I mentioned in the previous slide. The second is robustness and in-field update. In OTA update in the field, there is some risk for unintended update interruption because of sudden bury code disconnection, etc. In such cases, detecting the interruption and restoring the original code are needed. One idea is to use OTA start and end flag bits for detection. System can know the interruption if the start flag is set and the end flag is not set. And if there is a full backup of the previous version code, we can use it after the next time boot. Please note full backup needs twice larger memory density. The third is secure updates. We need to block software tampering by authentication. For example, an anti-rollback control is generally implemented to prevent the recovery of vulnerabilities in old version software. Next, I would like to introduce one idea to reduce memory density overhead for OTA. This idea is applicable to complementary memory configuration, in which one logical bit or data is stored by two memory cells to improve reliability, such as data retention. In OTA operation, the inverted relationship is temporarily released, and a new code is programmed in the area that originally stores the inverted image. In this scheme, the two cells per logical bit configuration needs to be restored within the data retention lifetime of one cell per logical bit. It should also be noted that the backup data of the previous code will be finally disappeared. If those side effects are acceptable, this scheme can eliminate memory density overhead for OTA. So, I would like to summarize this tutorial. I discussed the basic concept and supporting key technologies for automotive system design, case, and EE architecture evolution with vehicle automation were introduced. Computing for automotive ECUs includes infotainment and vehicle control, which are handled by SoCs and MCUs, respectively. Domain-specific architecture achieves high performance and lower consumption. Networks are evolving as cars become more automated. In-vehicle networks are adopting standard technologies such as Ethernet, CAN XL, as the amount of information increases. Security becomes increasingly important as networks evolve. Connectivity-based services such as maintenance upgrade with OTA will become commonplace, and automotive IoT will advance. Automotive technology and semiconductor technology have mutually enhanced each other in the past and will surely do so in the future. I hope that this tutorial will be an introduction to further advanced automotive technology. Here is a list of papers which will be presented in ISS Sushi 2023. This advanced forum, the power behind electrical vehicles, accelerating the future of automotive technologies, also takes place in this conference. And these are the references I used in this tutorial. I'd like to thank you, Dr. Kondo, ISS Sushi ITPC members, and my colleagues at Renesas Electronics who helped with making this tutorial. Thank you for listening to this tutorial.